Thanks a lot for the invitation and the organizing this very nice program. Today I will tell you about this topic which has been occupying my attention for the last few years. About studying the transport properties of interfaces in CFT and more recently we trying to extend away from the conformal fixed point, as I will tell you. And it started with this paper of 2020 with Costas and Shira that Shira talked about in the workshop. I don't know how many of you were there. In 2022, we extended with Stefano Baiguera and Tal Schwarzman to a more general construction using multiple brains, and eventually it can be extended to smooth geometries in the holographic context. And then in this paper of last year with Avik Banerjee and Ayam Kopadiai, we developed another technique using a perturbation expansion in the tension of the brain, and we discovered a new class of solutions that could be used to break conformal invariants. And then there's some work in progress with the same collaborators and also Tana and Kibe, where partly we continue exploring this class of solutions. And with Avik Banerjee, we are also investigating the breaking of conformal invariants by the T-bar deformation. I will try to explain all of this if the time allows. So to remind you what we want to do first is to consider conformal. So I will first study the conformal case where we have a 2D CFT. Well, 2D CFTs, two different ones, and they are separated by an interface, and we say that this interface is conformal when the T minus T bar component of the stress energy tensor on the two sides is continuous. So this follows in the case where the defect is put on a straight line by the word identities of the preserved symmetries, which are the time translation and the dilatation symmetry. So these are enough to show these two word identities. And so in general, you don't know, people don't know how to classify all the possible solutions of these conformal boundary conditions, except in the case of minimal CFTs. In that case, sorry, not even then. For minimal CFTs, one can classify boundaries, but not interfaces, because the crucial difference between a boundary and an interface is that you can see it by in the folding picture. If you fold the two CFT on the same side, so that this becomes a boundary, but it's a boundary between a theory which is a copy of the Hilbert space is doubled. So even if you start from a minimal model, once you double it, it's no longer a minimal model. So even for the, say, C=1 free boson, we don't know all the conformal boundary conditions. We only know a special class of those that preserve the current. So when this condition is implied by the simpler condition to solve on the currents, which is just the derivative of phi. And this condition on the current is simply solved by a matching condition, say the T and the X on the left are related by some matrix. So for this simple case of linear boundary conditions, of course, the theory remains free and you can solve everything. Well, fine. one finds that there is one parameter family of matrices which satisfy the conformal boundary conditions, and there is an angle essentially in terms of which one can determine all the properties of the interface. But what are these properties that we would like to determine? One property that is commonly studied is the boundary entropy or interface entropy, also called the Affleck-Ludwig entropy. If we fold it so that this becomes a boundary state, then this is defined as the overlap of the boundary state with the vacuum. So this contains some information. Intuitively, one can think that it should characterize the number of degree of freedom that are present on the interface, but it's not quite like that, because this is not an integer number. It can be any real number. And for more physical way to see it is to consider the entanglement entropy of a region between between the entanglement region from one side of the interface to the other. So in the CFT vacuum, this would be the result for a region of length L, but when there is the interface, this acquires an additional dependence, which is this G factor. So actually, this is true, and this is true for a boundary. For the interface, actually, what happens is this gets also modified when was found recently by Andreas Karch and collaborators and Doluri. Yeah. So there are two cases. When the interval, well, let's say three cases. The two special cases where the interval is symmetric. In this case, you can fold and you go back to the boundary case. Or you have the other extreme case when the interval is only one-sided. Now, the general case, I will talk about it at the end of the seminar, actually. But, well, basically, it's not, it's more complicated. Now we have two lengths, and the result is a non-trivial function of the ratio, which should interpolate between the two. So this, yeah, the other quantity which is important for, which is the one I will study, is this energy transmission, which is encoded in also one coefficient, which can be expressed in different ways. So if you are in Euclidean, you can consider the correlators of stress energy tensor across the interface is given by such an expression, which is fixed by the symmetries up to this coefficient, and then the T let's say on the left or on the right is T left right of minus A over 2 . So if you compare with the case of the boundary, in the boundary there is T bar is present, which is not there in the vacuum, but the coefficient is not modified. Whereas in the case of the interface, there is this new coefficient which appears, and in a paper by Maineri, Penedones, and Rousset, they related this coefficient that is defined in Euclidean in the Lorentzian picture by taking the CFT in the Lorentzian and setting up a scattering experiment. In this way, you take an operator this creates a wave packet or some excitation that travels through the interface. Then you see that it is partly reflected and partly transmitted. There is the transmitted part. You want to measure it by looking at the flux of energy at infinity, at null infinity. So this is done by looking at the so-called ANEC operator, which is the light cone, the integral on the light cone direction of, say, t plus plus. So if this is the x plus direction, this is independent of x minus, which means you can measure it at any light ray you want. You push it to infinity, you can see that this has the interpretation of collecting all the energy which comes to null infinity on the side, which is, since there was no other energy emitted, you can consider it as the transmitted part of the energy. So formally, you define the transmission coefficient as the limit when t goes to infinity, because you want to send this to infinity to create something like an asymptotic state. And there are technical reasons for so that this becomes a well-defined quantity. So you take the VEV of this operator in the state created by this operator, and you divide it by the left one. So in this ratio, this has a well-defined limit, and it has the interpretation of the transmission of energy, and one can show that actually it's related to this coefficient defined here in Euclidean in a simple way. It turns out to be just A over C. Well, in the case where the CFTs are different, so they might have different central charges, I have to find coefficients from the left-right or right-left. So this would be the T left, which is the transmission from the left. Then it is A over C left. And of course, tau right will be A over tau right. And so, yeah, and so you have this relation that C left, tau left is equal to. It could be any local operator, so yeah, that's a good point. In principle, this coefficient, it's not clear that it should be independent of this operator. So that was part of the paper that they showed actually it's independent. And the simple way to see it is to consider the special case when this is a holomorphic primary operator. In that case, the proof is very simple because actually this it just becomes a local thing. There is no dependence on space, so you can drop the integral and just see that basically what happens is that you have these two operators inserted on the left. Let me do it here. So when O is an holomorphic primary, you can use the OPE. And compare these two quantities, which is before the integral is what enters in this and for this quantity, well, both of them have the O on the left side, so you can go to the limit when you can fuse them. You can use the OPE, so O left will be fused into the identity or something which contains the stress energy tensor, plus possibly other contributions. But when well, on the left, it's clear that this is the only one which contributes to this 3-point function. On the right, you might wonder, well, maybe there are other other operators which mix with t right from because of the interface. So, but that doesn't happen. One can show that the preserved conformal invariance is enough to ensure that if this field has a two-point function with tr, it must be t left, or at least it must be a spin-2 holomorphic field. So in the case where there are no other than the stress energy tensor, then also the same contributes to this one. Then you can see that basically it's all kinematics, and the only dependence goes from this coefficient. So this will be determined by this, and this will be determined by this. All the kinematics is fixed by the holomorphy and conformal invariance, and the ratio is just given by this coefficient. So in this case, you can see that all the dependence on the operator drops out. But actually, it's not only true for conformal primaries; it's true for any operator. But you have to work a bit harder to show that. Now the positivity, because it's known that this operator is an operator which is positive, so which means its VEV is positive in any state. This implies some bounds that the transmission coefficient is bounded. It's bounded by 1. That's trivial. It follows from unitarity, but there is a stronger bound which comes from Anek, which is this one. Well, obviously stronger when C right is less than C left. So this means that if the left theory has bigger central charge than the right theory, you cannot have perfect transmission. So it's like you have a big theory. It cannot transmit all the information or all the energy to the smaller theory. Simply, these quantum bounds will prevent this from happening. That well means if I normalize such that here I'm sending a unit flux of energy, then the flux of energy I will see at infinity will be, so it's the fraction of energy which is transmitted across the interface. So it's in principle it should not be just a number. It could be depend on any kind of details of the incoming wave packet. So if you see it in solvable models, not non-CFT, but like a beam splitter or so, you will see that in general it depends on the frequency, it depends on, it might be a non-linear function or so, but so all these complications are absent, and in the CFT you just have a number. Yeah. If you have a marginal family, yeah. Well, that's the point. It's a new piece of data which is on top of the bulk theory. It's just associated to the defect. So it's in the bulk theory, you have the central charge, which completely determines all the correlation functions of the stress energy tensor sector. So you have this universal sector, and it is just given by one number when you have no defect. When you have a boundary, nothing changes. The same number, central charge, determines all the universal sector. With the defects, it's not true anymore. There are two numbers. Well, there are actually many more numbers. This is basically characterizes all the correlation functions at the level of 2 and 3 point functions of the stress energy tensor. One can show that from 4 point functions on, there will be also new coefficients. So this is kind of very partial. But so we know this coefficient is universal. We don't have any information so far about the higher order coefficients because they haven't been analyzed.
In the case of the boundary,
A, there is no A. There is no right side, so there cannot be an A. And the 2 point function of TT bar is just C over 2. So there is no other coefficient. What do you mean? Like it's a yeah, it's something. Yes, it's similar. It's a one property of the interface, but it's different from G. So one difference is, well, for G we don't know it's universal, but what does it mean? What does it mean? There is no meaning of universality for G. This coefficient has this property that is universal, meaning yeah, independent of the operators that you use to define. And on the other hand, for G, we have a G theorem. So we know it's monotonic under RG flow. For these coefficients, we don't know. So that's part of the motivation why I wanted to study what happens when you break conformal invariance. It's related to the displacement two-point function. Yes, it's also related to that, yeah. Well, the displacement operator is a combination of components of the stress energy tensor. So, and these two determine all the two-point functions. So it will also appear in somehow in the D. Yeah, so in the displacement operator, which for people who don't know, it's given by the broken word identities, so by the defect. So the energy tensor is conserved except on the defect. So the word identity picks up a delta function contribution with an operator in nu, but in 2 dimensions, nu has only one component. It's only normal. So I'll just call it D, and the two-point function dd will be is an operator that lives on the defect, so it has the same dimension as the stress energy tensor. So it will be like this times a coefficient CD, and CD, of course, in a well-defined theory, it's positive. So, but this is nothing but the unitarity requirement that tells you that tau is less than 1.
So this A, I wasn't sure I understood the answer to Andy's question. So this A depends on if I have like a marginal operator, exactly marginal operator, I can integrate along the defect. The A will depend on that.
It should depend on that, yeah.
And can you sort of explore like what range? Like, are there some bounds like that you can explore using that deformation? Could you explore everything in this bound 0 to min? Or is this a model dependent question? Or
I haven't done any perturbative. So one thing you could do is, yeah, to start with the defects. But as I said, there are not so many explicitly known examples of defects that you can study exactly, and even less that you can add perturbations to it. And so yeah, we are very limited in what we can do, and that's why we turn to holography, which is a arena where we can do many things exactly, although with the limitations, of course. But okay, to give an illustration, you have this is another sector, right? Now you have operators, so there is some kind of global symmetry. Then there are tilt operators, I think they're called, and but this will be a different story because it will be in a different sector. Of course, you can do many more things, but what I'm saying here is only just restricting to the universal stress energy tensor sector. Oh, that's an easy, right. Yes. So yeah, I think people recently, there was a recent paper, I think, by Mengel Paulos and also previous using bootstrap techniques to constrain the 4-point function, but they're not doing for 2D CFT, they're doing for line operators in higher dimensions. And you can use the broken word identities of this global symmetry to put constraints on. But it's,
I mean, wouldn't you expect that builds will not change the answer to A over C left? Because aren't you just exploring like different directions and like symmetry breaking space? Like I would imagine that it wouldn't affect this ratio, but I don't know.
it's a good question.
Okay.
Yeah.
Be a universal answer. How would A depend on those particular?
Yeah, I have nothing to say about that, but let me go on because yeah, I wanted to tell you that in the case of free boson, as I said, there is an angle which basically tells how these currents are rotated when you go to the interface, and then you can find that that this tau left, well, if you take C equal 1 on both sides, tau left is equal to tau right, will be given by cos squared of this theta. So you can see that you can explore all the range of tau very simply. And this is, it's like a marginal coupling, or it's conformal for any value of theta. You can also find the G factor for, actually that's an important point. The G factor, it's not only a function of theta. In a case of a free boson, if it's compact free boson, you can have windings, and you can have some winding modes associated to the defect as well. So when you match on the defect, you also have to match the winding modes, and you can do this in by matching the winding number in non-trivial way, sort of introducing an SL2Z transformation. So in fact, this G factor will not depend only on theta, but also on the winding numbers. W, well, there are some other properties. So this is important because it shows that these two are in general independent data of the defect, which is obscured when you go in the holographic description, because in the minimal setup for holography, what we do, we just take ADS3 for the holographic dual of the theory. Yes. Sorry, I was going to say that, and then I didn't say it. This is sometimes called the detailed balance condition. Well, the only physical, or the most physical way I know how to interpret it is to say that if you put the theory at finite temperature, so you have the CFT, you can put it at finite temperature, and you will find that there is a flux. There is a flux of energy, of course, depending on this transmission coefficient. Now, if the temperatures are equal, you will find that the flux should vanish by thermodynamic equilibrium. And this condition will not be satisfied unless this is true. So this is necessary to enforce thermodynamics. But it turns out it's true automatically, so we are happy. We don't have to do anything. But if you didn't know, that would be a way to derive that this condition has to be true.
But here you don't need temperature.
No, you don't need temperature. So this is independent, but I think going to finite temperature gives a nice physical interpretation of why this condition. It tells you how the transport of energy from one side has to be related to the other side. There cannot be an independent transport from the left and from the right. So it's kind of parity conservation, or I don't know exactly, but yeah.
Just make sure. So in that setting, where is CA or CR being measured? You have like a 2 CFT, right?
2 CFT with different central charges. And so there is a transmission one way and the other way. I'm talking about non-chiral theories, so CA, yeah. For chiral theories, I should say you can only have topological defects because yeah, when there is no T-bar, then you can see that this condition becomes, conformal boundary condition becomes the same as the topological one, so all this discussion does not apply. Which ones? Oh, it's proven because I know what is TL. It's this, so you can just see that CL. These are both the same as this parameter A. There is a single parameter. A is defined like this, so it involves both theories.
You can get it just from T-left.
Yeah, you can get it also like this. But anyway, there are some set of consistency conditions that just comes from conformal invariance. The statement is that there is only one new parameter, not more. So that's what's behind all of these equalities. I'm going a bit slow. Yeah, I want to go to the holographic setup where we use this minimal model, minimal not in the sense of CFTs, but minimal holographic model. Yeah, every time you have a defect, there is always this confusion because left can mean left movers or left theory. So I always use left right to mean the left theory, not left movers. So in holography, we have this, let's say we have ADS3. This is the boundary. In the constant time slice, we have X and Z, the holographic direction. As was done by Takayanagi, I think in 2011 or something, or earlier, you can model a boundary CFT by taking a brane. Nowadays, it's called the end of the world brane, which one can show that there is a solution to Einstein equation when this brane is on along a straight line in the bulk, and this theta angle is determined by the tension of the brane. So I call it sigma, and this is related to where L is the ADS radius. And then he used this to compute the G factor just by computing the entanglement entropy with the Takayanagi prescription. And so you can see that the G factor is a certain function of the tension. Well, log G is not the entanglement entropy. You have to subtract the vacuum contribution. But anyway, this is the G factor. And then if you want to do a defects, you have to glue two such things. So you have another side and another brane, but you have to identify the two branes by imposing the Israel matching condition. So there will be induced metric that have to be equal, and the extrinsic curvature on the two sides should match up to the brane tension. So by solving this condition, you find that there are two angles here. And they are related, and again determine So once you know the tension, these equations determine the two angles for given values of the left and the right, which are related to the central charges of the left and right theory. And the tension cannot be arbitrary. It has to be within certain bounds. Which comes from a certain stability conditions, and these bounds are important because then we will see that they translate into the annexed bounds on the transport coefficient. So now in this setup, we can construct the holographic dual of this scattering experiment. And I don't go into all the details. It's a bit technical, but the important thing is to count the number of degrees of freedom, because naively you would think that what can happen. So what am I doing is now I'm taking an excited state on top of the vacuum, where I have here some energy, which I can introduce by modifying the Pfefferman-Graham expansion by introducing a wave for the stress energy tensor in the form of a wave. And then on the other side, I want to have an incoming wave and a reflected wave. And so I have to solve these conditions where the metric and the extrinsic curvature are now perturbed. And I know exactly the metric in the bulk, so all I can change to satisfy these conditions is the data of the brain. What is the data of the brain? There is the brain will respond by fluctuating. So there is the profile of the brain. But then we find that in general, you cannot satisfy the equation simply by fluctuating. You also have to allow for a reparametrization or a certain diffeomorphism between the two brains that have to be identified. So before the identification was straightforward, but now it will require to explicitly introduce a reparametrization, which introduces two new functions. Let's say zeta and lambda, or zeta x and zeta t, which are the reparametrization of the coordinates on the brain. And now with these four functions, you can see that you can match all the equations. And importantly, we want Dirichlet boundary conditions on all these fluctuations. So it means they should all go to 0 at the boundary, the conformal boundary of ADS. So for x left, x right, it's quite obvious. This is the position of the defect at the boundary. We don't want to change it. We want to change the state of the theory, but the defect stays there. You could also deform that to turn on the displacement operator, but that would be a different computation. For this, it's not quite obvious, but turns out you need some boundary conditions. So that seems to be the most natural. And you find the unique solution. Not quite. You still also need some condition in the infrared. And because there are waves propagating along the brain, induced by the waves in the bulk, the most natural boundary condition to impose is that there is no incoming energy from infinity. Similar to what you do when computing quasi-normal modes in a black hole, you impose that there is no outgoing energy from the horizon. Here the horizon has at infinity. This gives an additional condition that you need to fix uniquely the solution. And once you do, once you have the solution, you can then read off the fluxes and find the formula for the transmission coefficient, which is quite simple. And one can show that with the bounds I gave before for the tension, you can find exactly that this tau precisely stays within the Anneck bound when the tension stays within its gravitational bound, which was not entirely obvious a priori. Yeah. Very good. This I cannot see it in the gravitational computation directly or indirectly. I don't know how to see it. Yeah, but there is no field here. I just consider pure gravity. So whatever field there is, I hid it away, and I'm saying I just look at the state. So I directly put all the energy in the stress energy tensor sector. So I've sidestepped the question how you create this excitation. And indeed, I don't know how to see from gravity that it's universal. It's something we have been thinking about for a while, but we have no idea. Which one? Here? So the profile of the brain is given by a function of z and t. So z and t are coordinates on the brain. And you want to allow a reparametrization between one copy of the brain. So it's a map from zt on the left to zt on the right. So there are 2 degrees of freedom in the opposite two-dimensional surface.
That is exciting some volume scalars?
No, there is no volume scalar. Well, these are vectors, if anything, but in fact they are completely fixed by once you impose these boundary conditions. But later they will become dynamical. So just wait for a minute. But so far, yeah, they are just fixed. Once I have the Bach solution and with all these boundary conditions, there is a unique overall solution. So okay, one other thing. The limit of perfect reflection means the transmission goes to 0. This requires, you can see from this formula, that the tension goes to infinity. So if you want a factorizing interface or something that has complete reflection, this can only be achieved in the infinite tension limit. And in turn, this one can show that this requires that the central charge has to go to 0 on the other side. So this is consistent with the bound also.
The infinite tension means that the position of the brain takes some specific position. Vertical.
Yeah. Yeah, it goes to vertical, but you have to tune at the same time the central charges, otherwise. It's not vertical, no. You have an infinite plus, but in the way you take the limit, there is a finite part which can survive and tell you the angle. So in the BCQFT, in BCFT, you still have this angle, even though the tension is infinite, but it's basically very normalized, if you want, tension that tells you the entropy.
The BCFT, can't you always get a perfectly reflecting interface by just taking a CFT with a boundary, and then I have some other CFT with a boundary?
Yeah, sure.
And then I just shrink. So do it doesn't require anything on the central charges. Maybe I misunderstood. Did you say something that in CFTs had to be?
Not in CFT, in this setup, in this holograph. To get it reflecting factorizing interface from this construction, I need to get, yeah. And of course I can superpose then another one on the other side, but that's cheating in a way. It's like this is tau left. So now you can reconstruct what is A by knowing that this was what was A over C left. Yeah, and C left is L left. So you just take out this factor.
A is a thing in parentheses.
Yeah, yeah.
It seems to depend depend on C left and C right. It has 1 over L left and 1 over L.
Yeah, but the tension is also arbitrary, so you cannot. That's the one limitation of this model, is that there is only
There's one parameter that controls
there's
everything.
one parameter which controls everything. So in particular, you cannot distinguish the G factor from the transmission. But you can elaborate on this by using a nice idea of Karch, that you can introduce more brains. So you can now have something like this. There is an ADS left, an ADS middle. And this ADS middle just shrinks to a point, so it's just associated to the defect. And this allows you to introduce more parameters associated to the defect. So you have still on the there is still only one transmission of energy, but now there are, so you can see there is a theta left, theta middle, theta right, and you can see that now you can decouple the G factor from the transmission. They become different functions of these parameters, so you can see explicitly that there are different parameters.
I was more concerned that, based on this model, it seems to depend on some bulk data, C left and C right.
But what does it mean?
Define those independent of sigma. Also, another question was like, what about top-down models? Because they don't look, most of them don't look like this.
No, but so that's our paper from 2022. Once you have introduced 2 brains, you can introduce 3 and so on. And then you end up with a pi geometry where you have many slices of pi, and you can take a continuum limit where it becomes a smooth geometry, and you can engineer it to reproduce a top-down solution. And then the nice thing is that actually what Karch showed is that the reflection coefficient in this case, it obeys the same formula. It's the how to say it, is tau of sigma 1 plus sigma 2, where this is given by the same function. So for the purpose of energy transmission, the tensions are just add up. So this transmits energy the same as a single brane with tension, the sum of the two. In particular, it's insensitive to this middle central charge, which does not appear in this computation, but should appear somewhere else. And when you take the continuum limit, you can integrate. So you can define, if I have a warped geometry, a defect geometry, which is of the warped I can discretize it by cutting it in slices and defining a fictitious tension. And then one can show that this fictitious tension is related to this A. I don't have the formula right now. I think it's maybe 1 over A squared or something. So that by integrating now the work factor over space-time, you get the effective tension, which controls the transmission in these geometries. And this can
the same tau with that effective tension.
Yeah. So this allowed us to compute the reflection coefficient for a Janus geometry, which was difficult to do in the honest way because you have the scalar also in the other fields. You have to fluctuate all of them. The Einstein equations become much more complicated, whereas with this trick you don't have to compute anything. It just gives the answer for free, so it's looks like magic, but of course it only works. So this geometry is supported by a single scalar at least. It needs at least one scalar with some potential. But of course you can have also top-down models with more scalars. And then more scalars, the solution will generically break more symmetries, and so you don't have this foliation. Don't have this nice foliation anymore, and then we don't know how to do it. Maybe one has to introduce more brains or some other configuration. Yeah, we haven't explored that. Yeah. Here? No. They are all different. They're all different, but so yeah, here let's say there is a radius and there are tensions. They are not all free, so there are some relations, but you have the freedom to reconstruct essentially any solution of the scalar fields with any potential. Yeah, so the effective tension, you can write it as an integral over 1 over a squared, or using the Einstein equations, also something like integral of pi prime squared. One or the other expression can be useful in depending on the cases. So yeah, one thing is that the G factor instead does not satisfy this composition law. So the G factor of the combined system is not the G factor of the single brane. So the G factor will depend also on the central charge in the middle, which is obvious because when you consider the Yuta-Kanagi surface, it will pass through this region, so it will know what's inside. But these two facts combined will tell you that there is a kind of non-trivial fusion of these two interfaces, which properties we don't know exactly because well, one thing one could do is try to compute the Casimir energy associated to this fusion. But to make it finite, one has to do it in global ADS, otherwise you have infrared divergences. So yeah, it's a bit tricky computation.
Do you know if the additive property for the transmission is special to holography?
Yeah, it's special to holography. Yeah, at some point I thought, maybe that's a nice way you can define an effective tension for any defect in a CFT, which has this additive property. But no, it's not true. And you can see a counterexample is already in the case of a free boson defect does not satisfy this.
Yeah.
So yeah, it's a property of a large C limit or holographic. I don't even know. One question would be, of course, you can decorate this model in different ways. For example, you can also add fields on the brane only. You can add degrees of freedom on the brane, like a scalar with certain potential, and then see how this depends on the field and if the additivity goes through in that case. We don't know.
Is this result independent of any action on the brane?
Well, I have only considered the standard Nambu-Goto action, so it will change if you add more degrees of freedom. Yeah. Okay, I think I should maybe consider. I said before that it was crucial to impose these boundary conditions to get a unique solution, but it was not completely a priori obvious that it is necessary. And then in this paper, which we started by quite different motivation, we were asking this question if, since we know that in gravity, I can get the motion of a probe particle is given by a geodesic equation in the geometry. This is not an assumption, but something you can prove just by Einstein equations taking the probe limit. So we wanted to know if the same is true for a string, if you can derive from Einstein equations that a string in the probe limit will satisfy the non-Bogotó equation. And just from gravity, so that means that non-Bogotó equation should arise as a consequence of the Israel junction in the limit when the tension goes to 0. And surprisingly, we found that it's not always the case, but it's true. In 3D gravity, we can show it, but in higher D, no, it's not true. So what does it mean? I don't know, but at least in 3D gravity, it has some holographic implication because so basically what we do is we take the same setup, but now we take a perturbation expansion in the tension. So we consider the case where the tension is very small. Now, when the tension is 0, strictly speaking, there is no brane, and that means these conditions are empty. And in principle, you can put a 0 tension brane anywhere you like. But then it turns out that if you start from any kind of crazy solution, that the perturbation theory around lambda equals 0 is not well defined. You have to start around the trivial solution, which is just x equals 0. X equals 0. Then we plug this in, and you expand in. You take lambda or sigma, the tension to be. You take sigma to be something of order epsilon, so infinitesimal, and all the fluctuations to be of order epsilon. And then indeed we find that so there are two modes. Let's say maybe I should erase to make it more clear. There are two modes, the symmetric and the antisymmetric one. And then the same reparametrization modes. So we still impose the Dirichlet boundary condition for these two, but not for the other two. So what happens is that for XS, it satisfies the non-Bogotó equation at the linearized level. Then it will be corrected at higher orders, but well, there is a part which will reconstruct the non-Bogotó equation, but there will be other terms which couple it also to the other modes. Then we have the antisymmetric part is determined once we know the symmetric part, and then there are some additional. Actually, what happens is that the Z reparametrization goes to 0 automatically as a consequence of the equations of motion. But ZT does not go to 0, and if you don't impose Dirichlet, this will be some function of the boundary time. Let's call it so to be more explicit. Yes. As as I said, the original motivation was not to study defects. We were just trying to understand this, how Navigato comes from pure gravity. But then we found that there is this class of solutions which can be used to enlarge the class of defects of the CFT, because there is no reason that you should impose this boundary condition. I mean, you want the defect to stay there, so these conditions are required, that the x left and x right should go to 0, but there is no very compelling reason that the reparameterizations also should go to 0. I'm trying to understand what it does. What are these? So there are. And now the nice thing is you can actually show that. So this excess. Once I impose the boundary condition, it will go like z cubed at the boundary. The next, so there is a constant mode which will be the source. I set it to 0, and the next is the web, and so there is some a of tau, a of t. And this mode T, one can show that it satisfies. Now again, I change a bit the setup, and I go to finite temperature. So I'm not doing this in pure ADS, but in the black hole background. Then one can show that this T satisfies the second order equation, where M is the black hole mass. So it satisfies the second order equation with the source given by this mode, which is like the wave of the displacement operator. So of course this has two zero modes and or two initial conditions, if you want, which we call alpha and gamma, and then a solution determined by this mode. Yeah, that's what I'm going to explain. So what is it? It is you have the defect, but you have different times on the left and right. So there is a time reparameterization here. It's T left, and so actually, if you go through the definitions, what happens is that T left is in perturbation is T minus this calligraphic T right is T plus this calligraphic T. So you can say that, well, anyway, there is a map of T right. It's a function of T left. So I'm allowing this reparameterization of time, which seems a bit strange at first, but then you realize that actually I can undo. I can trade this map, or I can cancel it by doing a one-sided conformal transformation. What is this? I do a conformal transformation on the right theory only, and I change x tilde plus and x tilde minus in light cone coordinates are the inverse of this. So I do the same transformation on left and right movers. This has the property that the defect is the location of the defect. The spatial x is x plus x minus equals 0, and also h plus tilde, minus is equal 0. So after the transformation, it's still is still at x equals 0, but it changes the conformal structure everywhere else. So, and of course, a half-sided conformal transformation is not a symmetry of the whole system. So in a way, what you're doing is you are trading this triparameterization by some state where you fine-tune some incoming energy. It's like you engineer some perfectly reflected wave packet in such a way that this cancels the effect of this reparameterization. And now, of course, this creates some state at infinity. So conformal invariance will be, in general, not preserved, but one can quantify this breaking, and you can show that the word identities are modified in the theory after the change of coordinates. So there will be basically a valve for the displacement operator. So you recall I wrote before the word identity in the normal direction. We'll have a source. We'll have some so it's the Schwarzian, and this you can identify with a wave for the displacement operator in this state. The most interesting thing, I think, is that another way to interpret this is to say that we have twisted the boundary condition, the conformal boundary condition. So before we can interpret the conformal matching, the conformal interface condition as a map which intertwines the Virasoro modes on the left and right. What this half-sided conformal map does is to introduce here a twist, some conformal map Q which depends on H. And so we want to suggest that this is like a generalized class of conformal boundary conditions that one can consider. And this is not very weird if you think about it, because when people look at brains in Vestominovite models, you can see that you can satisfy the continuity of the Sugawara stress tensor by twisting the currents with the automorphism, right? So you can have JA on the left is equal to some omega, where omega is some automorphism of the Katsumudi algebra, and this will give a conformal boundary condition. So we are suggesting that it's possible to do it directly at the level of the Virasoro algebra. And then one can ask, okay, if this is a conformal map, then this U will be just an exponential of Virasoros, something like this. And so it would be like an inner automorphism, but one could even wonder if you can even extend it further to outer automorphism of the Virasoro algebra, which will not allow this description in terms of a conformal map, but then I don't know how exactly to describe it. But, yeah. This is for the future.
Not the same as the West,
No, it's not the same, no.
That changed the condition of stress.
Yeah. This just leaves T invariant because omega cancels, so this will not change the boundary condition. But this U, so yeah, if you
Is there a way to write it in terms of the stress tensor?
If it is a conformal map, yes, but if it's not, I don't know. But I don't know enough about what is known about the automorphism of the Virasoro algebra. So one last thing I want to mention is that this map and also the zero modes here, which are not just determined by the non-Vogoto excitation, can be read off from the entanglement entropy. Well, there are some formulas. Maybe I will not bother you with the formulas, but but one question is, what is the role of these zero modes? Because they survive even in the limit when the tension goes to zero, and this is a bit strange, right? You have like a non-trivial reparametrization even in empty space, and you're just introducing a defect by nothing, just by this reparametrization. Is this physical or not? And we were wondering this question, how to settle this question. Is this a physical or non-physical? It's not very obvious. And the best we could come out with this is to say, well, let's see if it violates anything that we know. And because we had computed the entanglement entropy, we could check the strong subadditivity. So the strong subadditivity, as you know, it's the property that I have two subregions, then the entanglement entropy and so it's bigger or equal than zero. If you are in transnational invariant system, you can engineer this configuration where the divergent terms cancel, so that this is a finite quantity. So you take two regions that are like this, that are taken along the light cones of the union. This should end on the light cone. So this is A and this is B. And we use the fact that the entanglement entropy only depends on the causal domain of the region. Now, when you have a defect, you can have different situations where the defect lies here. So it intersects both A and B, or it lies only here. And so what we could see is that for any value of the at least the strong subadditivity does not put to the order we could compute in perturbation theory. It does not put any constraint on these zero mode parameters, which I erased. Yeah, this alpha and gamma, they are not constrained. So it seems that from this point of view, they are physical parameters, and one could construct a non-trivial space-time by gluing using these zero modes. So also this is a bit mysterious so far. How much time do I have? 10 minutes?
Yeah.
So now I want to tell you about this other way of breaking conformal invariance is by using the T-bar deformation. Who knows what is a T-bar deformation? Almost everyone, so I can be quick then. So what we need to recall is simply that the TT bar is given by a deformation of the Lagrangian, which is the determinant of the stress energy tensor. In 2 dimensions, if you go to conformal coordinates, this is TT bar minus theta squared, where theta is the trace of T. So when you are at the conformal point, when theta is 0, it's just TT bar. And this is an exactly solvable deformation. If you are in a CFT at finite volume, you can compute exactly how it changes the energy spectrum. So if you have it depends on the deformation parameter. Given by this explicit formula, in terms of the initial value of the energy at the undeformed point and the momentum, this flow equation can be solved exactly to determine the energy spectrum, from which you can see that in fact the theory is never completely fine. Sigma can be positive or negative. In each case, there are problems. For sigma negative, you can have complex energies. For sigma positive, you can see that at very high energy, this has a Hagedorn spectrum of states, and so it behaves like a string theory, or in any case, a non-local field theory. The behavior of the operators under this deformation can also be characterized by an evolution equation, where basically the deformed field evolves according to this equation, which has to be understood as something that you can put in a correlation function and try to solve order by order in the deformation parameter. And if you have a scalar field, if you try to do it at the quantum level, then this of course is a composite field which has to be regularized. And if you keep only the leading term in the OP, the leading singularity, then you can resum this and obtain the field, the deformed field at finite sigma. And this was done by Cardi in some paper. If you go to momentum space, this will behave like some cutoff. So there is this some kind of Brownian factor here, which is the interpretation that the particle, well, this is a field, but the particle undergoes some Brownian motion with the diffusivity, which diverges with the cutoff. I call it diffusivity because of this k-square dependence. So the particle tends to want to delocalize after the deformation. This can be seen also in many other different ways. Now there is a holographic prescription that to implement this TT bar deformation. It can be formulated either as ADS with finite cutoff, or with the deformed deformed boundary conditions. This interpretation was given by Monica Guica and Ruben Monten. I think it's preferable because it allows to treat both signs of the deformation. That's
So
fine.
here, are you considering on the CFT side the setup that you had initially with left and right? And
Yeah, I will.
T-bar back?
Yeah, that's what I'm going to do. But first I need to both sides. Yes. And it turns out that you cannot turn independent TT-bar deformations. There is also there a sort of detailed balance, which comes about in a different way, but the deformation parameters have to be related to the central charges. You can see it in ADS by saying that the cutoff has to match, because the cutoff is basically given by C times the. Okay, let me say what is the prescription is that if you do the Pfefferman-Graham expansion, famously in ADS it terminates at order Z squared, and the standard prescription is that this is the boundary metric. This is the wave of T, so I call it T0. Now in the deformed boundary condition, the boundary metric is G0 plus mu G2 plus mu squared G4, and the deformed stress tensor is G2 plus mu G4. Now these two prescriptions are actually compatible because you can see that putting the theory at finite cutoff and then looking at the metric induced on this cutoff surface will give exactly this boundary metric. But as I said, only for one sign of mu, this makes sense. So you can relate mu to the deformation parameter of the theory as minus sigma times C over So now if you have two different CFTs and you want the cutoff to match, you have also to adjust the deformation accordingly so that you have a single cutoff on both sides. Now this can be repackaged also as a kind of flow equation for these quantities. But I will not write the flow equation since this already is the solution of the equation. But the important thing to know is that this variation, this deformed metric, can be re-expressed as a change of coordinates. So this is this deformed metric can be reabsorbed in a change of coordinates. So if you do if the original coordinates are say inlet cone, this is the standard flat metric, then one can see that G mu or gamma mu, I call it. The deformed one will be the same in some coordinates, where these coordinates are related to the original one by a certain transformation. Where H and H bar are related to the stress energy tensor, so T. The light cone coordinates are mixed, and the mixing is given in terms of the stress energy tensor. So this is a state-dependent coordinate transformation, which allows you to to bring the metric to flat space again. And so basically this is the trick that we use to study the defect now, because so once you have this change of coordinates, you can reduce the stress energy tensor, and this is fine for the vacuum or the theory without defect. But now what happens if there is a defect is that this conformal transformation will not preserve the defect. It will not preserve the defect, so you have so the original defect, let's say in the UV plane, you have the defect at x equals 0. X is v minus u, so you have then you have some excitations. Now you go to this UV plane where the metric is again the deformed metric is flat, but in these coordinates the defect now changes, so you can no longer match it. And then what you can do is take yet another set of coordinates where you just use conformal transformations to bring it back these two straight lines. And you have to do it separately on the left and the right side. So this u tilde, v tilde are now given by, it's just conformal transformation. No. No, the TT bar breaks the conformal invariant. So that the whole point is to have a setup where you have a controlled breaking, well controlled. It's a solvable model, but you can break conformal invariant. Well, you know what happens. So that, no, this is in the conformal theory. What do you do it? So you have to fine tune this conformal transformation in such a way that after you do the TT bar deformation, you recover the straight line. So you will get some relations that this alpha, so you have 4 functions, alpha left, alpha bar left. You have 4 functions that you have to determine in terms of the components of the stress energy tensor, so that now that in these coordinates, actually you want this to be flat in this coordinate. So necessarily here it will not be flat. But you can do it order by order in perturbations. So what you want is that x is v minus u. So the normal coordinates in these flat coordinates are, you have 3 conditions. Which says that the defect is a good defect in this flat coordinates. And now for the moment, I'm not talking about this possible reparametrization of time. So I'm just imposing that I have a continuous time on both sides. Now it seems that that's not enough. I have 3 conditions for 4 functions. So there is a redundancy, but this is expected because there is a redundancy also at the level of CFT. I can do a global conformal transformation that doesn't change anything. But this will, it gives a consistency condition, because so this redundancy I can keep it there and see that it doesn't affect the final result. And then I have some, so yeah, as I said, these are the components of T, the original coordinates. I can then find the light cone coordinates of the deformed stress energy tensor. It's given by some expression. Something similar for TVV. And so what one can check after you solve these functions, you plug it here, and you check that t minus t bar, the deformed one, is continuous. To first order in the deformation. So if, as I did in the conformal case, I do an expansion around the small fluctuations of the stress energy tensor. However, at higher orders, this is no longer true, and this points to the fact that this flow equation probably is not valid beyond the classical level. So there will be some quantum corrections that nobody knows. So this would be a way maybe to determine what these corrections should be. But if we stick to first order, then before, in the conformal case, I can find the transmission coefficient in this way. I have this left and right modes, incoming and outgoing. So I can say that T, let's say that this is T TVV left, this is T UU left, and this is TVV right. So I can write that TVV left was the reflection times TUU left plus the transmission TVV right. And of course, this to sum to 1. So this determines, once you know the transmission coefficient, to read off the fluxes, or vice versa, if you know the fluxes, to impose this condition and read off the transmission coefficient. So you see what I've done is the logic is I start from a valid configuration in the CFT, such that it translates into a valid configuration of the deformed theory. So I know the fluxes in the deformed theory, so I can read off the transmission coefficient, except this relation will no longer be valid. What you find is that in general, this has to be modified by some function of the incoming fluxes, which will contain nonlinear terms and possibly derivatives of the fields. Now, in some situations, for example, when you have constant fluxes, and you can ignore this Schwarzian, or it doesn't contribute because it has derivatives. So one example where you can do this is if you glue two states at different temperatures, right? Then what happens? You do a quench when at time equals 0 they are joined, and because there are different temperatures, there is a light cone when something happens, and here you have this non-equilibrium steady state, which is a stationary state at late times with constant fluxes. So this was done in the case of CFT by many people, and now you can do it also with the defect. So you have to separate this nest region into a left and right part. But in each part, it will still be the case that the fluxes are constant and there is no time dependence because it's a stationary state. So in this situation, the Schwarzian does not contribute, and this gives a great simplification, and it allows you to find the solution to a certain order. So for example, I can go on to second order. So I'm finishing. And you find that this correction is given by this. okay, I will not give the higher order term, but the crucial features are already present here. So the point is that it's a nonlinear deformation of the matching conditions. It vanishes when x equal y, which is expected because it means, again, it's a sort of equilibrium condition. If the fluxes are the same incoming, then they should be the same also outgoing. It vanishes when either R or T undeformed is 0. So if you have a topological interface, obviously it will remain topological, and if it's a boundary also it will remain a boundary. And so yeah, it satisfies all the properties expected. So in perturbation theory you cannot see it, but in the next case we also did the computation numerically, and we show that it preserves the unitarity condition. So now when you have the Schwarzian term, things become more subtle, and we can only go to first order in the expansion, and this M becomes a frequency. So now there is a first order term. Now there is a frequency dependence, which explicitly shows the breaking of conformal symmetry. And this, so this is an exact formula, but only to first order. And what you can see is that, well, if you want this to interpret this as a deformed reflection coefficient, and you want this to be between 0 and 1, then this imposes a cutoff on the frequency. So it means you cannot do this experiment for frequencies above this this cutoff. Now this cutoff in frequency, as I said, was somehow expected for the case of a positive sign, because then you cannot exceed the threshold Hagedorn spectrum. But for negative mu, which is positive sigma, you don't expect that there is, at least in just from the spectrum consideration, you wouldn't expect this bound. So the meaning of this is not completely understood. But anyway, if you state within this bound, then you can plot this R as a function of mu in the allowed region, and you find that it's always a monotonic function. So you start from R0, the undeformed value, and it goes to, it always goes to from 1 to 0 between this in the allowed region. So it seems you can cover always all the spectrum of the allowed possibility. So yeah, that's all I have to say. This is still a work in progress, and we have to understand more the properties of this example to have a full picture. Thank you.
So with the TT bar deformation, you could get any reflection coefficient, you're saying?
Yes, from any initial one I can deform, but there is this problem of the allowed region.
The other thing I didn't understand is that maybe the answer to Andy's question, like in the BCFT, like at least if I have two CFTs, clearly I could do, let's say, a relevant deformation on each side, and then you get something that makes sense. Well, why can't I do a TT bar independent TT bar deformations on both sides? I mean, I understand they're irrelevant deformations, but you seem to suggest that you had to have a relation between
yeah, so, well, from the holographic point of view, the cutoff, if I take the cutoff, finite cutoff point of view, the cutoff is controlled by C times sigma, the deformation. And it seems natural that if I have two sides, I want the cutoff to match across the two sides. Otherwise, I don't know what I should do. So this seems to imply this condition. Also, if I don't do holography, so this flow equation argument with this sequence of conformal maps, it breaks down. It seems that I cannot solve these conditions unless I impose this relation. So somehow it seems necessary, although I don't quite understand why. I thought also initially that, well, I can take two deformations independently.